nothing. We should have done my plan. Our reminders are up on the center screen over the break. If you haven't got caught up yet, catch up on your Chapter 9 reading and then also start Chapter 10. We know that practice learn next week. Are there any short questions about that? What you thought? Good? If for some reason you're sick, you get in a car accident, you're stuck on the highway in traffic, you wear shorts for some reason, although it's supposed to be cold out, and you're not able to do your lab practical at the assigned time, immediately contact me. Send me an email right away. We will get you into another group, or we'll have you do it the week after, like Monday or Tuesday. We will make sure you have a chance to do that. So don't feel afraid or ashamed to contact me. Please make sure you do that. We know we have quiz 12 getting turned in. Remember, you can also turn that in via email by tomorrow at 1:30. I have to get some kind of deadline, otherwise it'll keep trailing in throughout the week. Quiz 13 is on Canvas. It is that scale placement quiz that you took at the beginning of the semester. It's just called something different. It's the exact same thing. It is for the research. If you consented via the consent form at the beginning of the semester, then we'll be able to use your data. If not, just taking the quiz earns you the points. So it is graded on completion alone. So opens on the 4th at 6 a.m., closes on the 11th at 11:59 p.m., 45 questions, 60 minutes, graded on completion. Remember with that quiz, for some reason a picture didn't show up right, just pick an answer and go on. I actually don't even go into it. It's really the researcher who uses it if you consented. If not, you just basically erase the data. Exam 4 we know is Thursday the 12th. By the way, the 11th, I saw the 12th. The 11th of December is the last day of instruction for any course this semester. The 12th is the study day, so no instructors can make you come in and anything like that, which means our last lecture is the 10th in this class. You do have discussions going through the 11th. 5:30 p.m. the 11th, 60 minutes, your usual exam room, 44 multiple-choice questions, cumulative for the semester. You walk out with a booklet. A key that has explanations, not just ABCDs, gets uploaded, and you can probably figure out your grade before I even have a chance to post it, but they of course also get posted. The final exam is on Monday the 15th, 11 to 1, Chem 110, not your usual exam room. This room, cumulative for the semester, there are 2 parts, each 40 multiple-choice questions, each for a time of 55 minutes, so please plan on being here from 11 a.m. to 1 p.m. Don't tell your boss you can work or something like that. Don't plan on getting out of that exam early. Are there any questions you thought of? We did add some electroactivity problems there and some new Moodle problems, and we're going to continue with section 9.4. So number 23, page 264 is where we're starting, and they define a covalent bond as a bond in which the electrons are shared by 2 atoms. That's from our textbook. Show this with Lewis dot symbols for 2 chlorine atoms and show how the electrons are shared. That's what I have on the top, okay? And what I've also, I kind of have in the middle of that page right there. So the electron being color-coded here helps you to see that in between the 2 atoms, once they're bound, we have an electron from each. So they're sharing. And they're doing this to get a more stable electron configuration. On the bottom, I have for part A, how this is different from the representation of any cell. There we're transferring electrons to get the more stable electron configuration, in this case for both the ions, but we're focusing on the chlorine right now. In 24, they want us to compare the electron configuration for chlorine in our diatomic versus in the sodium chloride, and that's why I have to top my page. They both actually have the same electron configuration, which is isoelectronic with argon. So again, all bonding occurs in an attempt to become more stable, meaning a lower energy electron configuration, and if at all possible, one of a noble gas. Any questions? In a way that kind of reminds us where we left off last Saturday at the beginning of chapter 9. How does this relate to that cat rule? Or, quote, an atom other than hydrogen tends to form bonds until it's surrounded by 8 valence electrons from our textbook. Both the chlorine have 8 valence electrons. Whether it's a shared electron or it's a transferred electron, they both have their octet. Now, not all atoms want to have octet. Notably, as mentioned, hydrogen. Hydrogen wants to be like helium. Therefore, I call that the duet rule. It wants 2 electrons. There are a couple others at times that don't like to have octets, and we'll talk about them later on, probably after the break. Okay, we do not octet Lewis structures in this class. Any questions before we make sure that we know what different electrons are? Hey, don't freeze on me. I forgot to click that in. It has octet row at the bottom. So we have what we call lone pair and versus bonding electrons. Lone pairs, and notice that there we have two different representations here. I will almost exclusively use the representation that I have on the sheet, which is different representations for our electrons. I show my non-bonding electrons as dots. And if they're in a pair, it's called a lone pair. I have to say if, because not all non-bonding electrons pair up, as we'll see in our non-octet structures. The bonding electrons I like to represent differently. Each line equals 2 dots, or 2 electrons. I found over the years that it helps the students' comprehension and understanding to make them distinctly different. However, if in the past you were told or taught to do it the other way, that's perfectly fine. You have no more free response work for me, so it's okay. I'm not here to reteach something you might already know. So if you want to have them all be dots, that's fine. Just make sure to be able to identify for yourself that which ones are bonding versus non-bonding. I forgot to click the bonding. The bonding part is actually at the top of page 265. I forgot to make a note about a page change. We're asked to review and complete our table for different numbers of electrons, type of bond, example of that structure for each. So I have our table here with 2, 4 versus 6 shared electrons. Type of bond, well, if we have 2, we would have a single line. Therefore, we call it a single bond, versus if we had 4, we would have 2 lines, because each line represents 2 electrons, in which case, a double bond. And if we had 6, we would have 3 lines, therefore, a triple bond. The examples I use were diatomics. There are many other examples you could think of. As long as you remember each line represents 2 electrons, we're good. And hopefully this is reviewed. Any questions? We're going to go now into something that I think is not review, and you may never have been taught or even had this brought up in a class before, and you may not have ever thought about it. Bond length, of course, is not always the same. We have a table where we have different types of bonds. You also have it on your page. It's on page 265. And we can see the length is measured in picometers. You do have a little table there to fill out. I do not have it on the slide. So let's put it together. We're comparing some very similar bonds, meaning between the same 2 atoms. So again, if we have 1 line, that would be a single bond. 2 lines, a double. 3 lines, a triple. Which tells us 2, 4, 6 electrons respectively being shared. If we go from the table, table 9.2 to this table and transcribe the bond lengths, for a carbon-carbon single, it's 154 picometers. A carbon-carbon double is 133, and a carbon-carbon triple is 120. Notice as we increase the number of electrons between the 2 nuclei, the bond length gets shorter. Is that just carbon? Let's look at a couple others. If we look at carbon-oxygen, single versus double, the double is shorter than the single, and the double has more electrons being shared. We can also see this with the carbon-nitrogen series. Single to a nitrogen, 143, a double-bound carbon-nitrogen, 138, and a triple bound is 116. This is not just a fluke. As the number of bonding electrons increases, wow, that's supposed to be a line like that, goes up, the bond length goes down. And that should actually make a lot of sense given everything we talked about in terms of electrostatic attraction. If we're increasing the number of electrons, we're negative charge between the two nuclei would be going up. Whereas Q plus would be staying the same, they're the same atoms. Well, if we increase one of the charges, we increase the electrostatic attraction. If there's more attraction, the atoms themselves, the nuclei, are going to get pulled closer to each other, which results in a shorter bond length, a shorter distance between the atoms. Any questions before we look at a real molecule and compare it to our table? On the next page, you have that molecule type for you. If we want to, I already had the table filled out for you, by the way, because I didn't want to make you flip back and forth, although we also have our table 9.2 up on the screen. So for our actual molecule, we have our experimental values being actually measured values. For carbon, hydrogen single, it measured out to be 109 picoliters. According to the table, it's 107. Our carbon single oxygen measures 131. According to the table, it should be 143. Our carbon oxygen double measures 125. On the table, it should be 121. And our oxygen hydrogen single measures to 95. On the table, it should be 96. Does anybody have any ideas as to the differences in the numbers? What's the first word in the head of the table? Average. Which means even the same number of bonding electrons, the same exact atoms varies with different molecules. We will actually bring this back a little bit once we understand some of those differences, but for right now, when you're looking at a bond length table, we do have to remember it's average. So our experimental values versus our reference values are not exactly the same. Think of the reference value as almost like a theoretical yield, and the experimental is like the actual. It's not going to be the same, but it should be close if you're doing well. So they ask you underneath, are the experimental bond lengths consistent with the Lewis dot structure? We looked at, they're not necessarily exactly the same as the table, but what about the Lewis dot structure? Well, our carbon oxygen single versus our double. It does go shorter when we go to the double bond. It's a shorter bond for the double, so that makes sense. It's consistent with the Lewis structure. If the measurements were like flip for those two, that wouldn't be consistent with what we were thinking about as far as our trends. Are there any questions? Yes? The same. The question was, how do we determine the values? Yeah, just make sure. The same way as we determine the size of an atom, experimentally in vacuum chambers, we're able to, let's say, have the gaseous molecule in there. If you do the right kind of vacuum, you get it to adhere to a solid surface, and you kind of trace the topography of that surface. So from your macroscopic results, actually, I did like a wavy thing last time, but I didn't actually draw anything. I don't think. So let's say this is the solid surface, and we have some molecules on here. Of course, we wouldn't be able to see them. We bring down a needle, which is able to interact with the electric fields. And let's say we had, like, I don't know, a diatomic here. We would bring this needle down, and we would go this way. What it would do is almost trace out the topography of the surface, which now is no longer flat. We put something on there, and from here to here, they can measure that bond length. So we're, again, using macroscopic experiments, assuming we're interacting with atoms, we know that our needle is interacting with electric fields. It has a charge on the needle, which is negative. So we get closer to the electron, it gets repulsed. So that's why it traces it out. So you can do this very same thing to get this. Again, as long as our theory keeps holding up, we figure that's what we're interacting with is atoms. We don't know because we can't really see that. Anybody else? That was a really good question. I did put number 30 in the lecture activity list because we're like switching representations again. Every time we have a major change in representation, there's usually a question as you think about why we would be maybe using a different representation, like a Lewis structure, versus space filling models, which they have you thinking about those two different representations, what information you're losing, what information you're getting, things like that. We're going to go on to think about the fact that not all covalent bonds are the same. On page 267, and this is something we're going back to hopefully electrons in a chemical bond. Therefore, it really does belong in this chapter. When we thought of electron affinity, we were thinking about the ability of an atom to attract towards itself just electrons in general, rather than free electrons being transferred from one atom to another in a redox transfer, something like that. Now we're thinking about it in terms of just the bonding electrons themselves. Okay? The trend we can see from our periodic table. Common abbreviation for electronegativity is EN. We can see that as we go from left to right across a period, we're increasing our electronegativity. And as we go up a group, we're also increasing our electronegativity, and that has the same explanation as electron affinity. Over bar nonmetals, we have higher effective nuclear charges, right? Because effective nuclear charge increase that way. Well, if the bonding electrons are feeling more positive charge from one of the atoms, they're going to be more attracted to that atom. As we go up a group, the distance between the nuclei will change because the size of the atoms is changing, right? And the atoms are simply closer to each other, meaning those bonding electrons are closer to the nuclei, they'll be more attracted. Ohm's law. Lower distance, increased electrostatic attraction. In terms of electronegativity, it was assigned in an arbitrary way, meaning fluorine was assigned as the highest electronegativity. That 4.0 is not based on any kind of measurement. It's just an arbitrary value that the person who developed the idea of electronegativity and the numbering system just assigned fluorine as 4.0. Everything else is relative to fluorine. Meaning, relative to fluorine, oxygen is a little less electronegative, but nitrogen is even more so less electronegativity. The number goes down. We can see that there should be, or actually that should be, is a connection between electronegativity and metallic character, meaning non-metals have higher electronegativity, metals have lower electronegativities. Hydrogen, technically, although it's way over the other side of the periodic table, slides in between boron and carbon because it is a non-metal. So if we're reading group 1, it has a relatively high electronegativity because this really is a non-metal. The reason why we have to think about the ability of an atom to attract the bonding electrons towards itself is because not all covalent bonds equally share the electrons. So I'm trying to show equal sharing versus some share the electrons in an unequal way, meaning one of the atoms has a bigger pull on those electrons. That's meaning a higher electronegativity. And this leads to a polar covalent bond, or what we call a polar bond. A covalent bond with greater electron density around one of the two atoms. Yes?
Does that affect the length at all?
What was that?
Does that affect the length of the bond at all?
Not really. We still have the electrons there. If they drag the other nuclei closer, that would be different. So what I've already drawn on the sheet is a really easy way for you to distinguish between nonpolar and polar. A nonpolar covalent bond is a bond formed between two atoms of the same element, because they have exactly the same properties, including electronegativity. A polar bond is a bond formed between two atoms of different elements, because they will not have the same properties and they will not have the same electronegativity. Although, the textbook author liked the round. If you took Chem 100 here, you worked with the Bauer book. And the Bauer book, if I remember it correctly, has 2 decimal places for electronegativity. These measurements actually go up to 3 and 4 decimal places. For some reason, I actually did argue with Chang when he was alive. Met him up at a conference and said, dude, I don't like your book in some places. Cobalt, nickel, copper, silver, mercury, all 1.9, there's a couple of others, all 1.9, they aren't. And that, I told them that gives students a very confusing view, that they think that there are elements that are atoms from different elements that have the same electronegativity, and they don't. It's lost in the decimal places that got rounded out. Although, if they have the same number right here, they're very close, they're not exactly the same. Which therefore makes students believe that a bond between two atoms with the same number on this table, let's say nitrogen and chlorine, would be a nonpolar shown to be polar. So this is a very nice, easy way. Two atoms of the same element bound, it's nonpolar. Two atoms of different elements bound, it's polar. Don't even think about the numbers because you're not going to be given the numbers on the testing situation. Any questions? We're going to look into this a little bit more. Ooh, that double click. They asked us to use HF to show this, so I didn't have the HF up there before. I wanted you to get the idea as to why I wrote that first. So we know for my favorite molecule of all, hydrogen fluoride, or if it's in water, hydrofluoric acid, which it kills you in unique and special ways. I actually had to teach doctors how to treat me when I had the HF spill. Fluorine, being the most electronegative, is going to have a large draw on the electrons, which is why in that electrostatic mass we have more volume where the highest probability of finding electrons is by the fluorine. We often will label that as a partial negative charge. It's not an ion, but it's kind of negative. And since the bonding electrons are hanging out closer to the hydrogen, that would be labeled a partial positive. It's not a cation, but it's got a little less electron density than you would normally think, because the fluorine is pulling the bonding electrons towards itself. Again, even drawing lines in our modern model is not really the best way to depict electrons. When we draw a line where, like I did here, I'm saying the electrons are right there. They're not. Remember, it's only all probability. Meaning, the electrons, even the bonding ones, don't have to be between two nuclei, which is how they get this electron density map. Susan was confused by the map before in the past. We also can do this, and you may have done this in a past class, with an arrow. It always has a little cross down there to distinguish it from other types of arrows. And I was never taught as an undergrad what the little cross was, how handy that little cross could be. If you cover up the arrow head, does that look like a plus sign? It always goes from positive to negative. Something I wasn't taught. I figured out for myself over time. I said, why not just tell people that? And the positive is always going to be the one with the lower electronegativity. The negative is always going to be the one with the higher electronegativity, meaning it goes from low to high electronegativity, and you can use your trend to figure out which one's low, which one's high. That was back in the 80s and stuff. They deleted line people a lot. Any questions before we fill up table on number 34? Because we're going to come to something like, wow, really? So now we've been talking about the fact that there are two different types of covalent bonds, and then we have ionic. But now we're going to get into the fact that actually there's a spectrum of bonding. First, let's just think about the type of elements, meaning degree of metallic character. Then we'll think about the electronegativity and the difference. But notice the fourth row is titled percent ionic characteristic or character. So yes, ionic, you tend to think of metals and nonmetals in general, right? Covalent in general, non-metal, non-metal, whether it's polar or non-polar. I'm saying in general, because in future classes you will see metals bond covalently, and you'll see some weird things. Well, in terms of electronegativity, metals have lower electronegativity than non-metals. So for our ionic, it should make sense that I just clicked in and it said I just merged those two words, low and high. Between the covalents, the two, there has to be some difference there to distinguish one as being polar and one as being non-polar. If we have polar, one of the nonmetals has to have a lower electronegativity. The other one has to be higher, kind of like the HF bond. If we have non-polar covalent, meaning we have two atoms of the same element bound to each other, they of course are going to have the exact same electronegativity. So it's equal electronegativity, so you can use your own words. You can think the same if you want. Often the difference in tour group, I have to wait. The difference in electronegativity is used often to distinguish between different types of bonds. Depending on the discipline, there are different cutoffs. So I don't teach cutoffs because it'll change when you go to organic chemistry, and it'll change if you take an inorganic chemistry class. So depending on the discipline, they have different cutoffs. But if we're thinking ionic, we're definitely going to have a larger difference in the electronegativity. If we're thinking polar covalent, there has to be some difference, but it's going to be small. They're not metals, they're still close to electronegativity. And if it's nonpolar covalent, of course, there is zero One number minus the same number always gives you 0. As far as the bottom of the table, though, it's a spectrum. That's why I don't like cutoffs anyways for distinguishing different types of bonds. We go from pure covalent, meaning 0% ionic character, to high, but not 100% ionic character, meaning low and not 0% covalent. So meaning if you have something that you distinguish as ionic, sodium chloride, that's ionic, right? There is times when the electron is actually being shared. Most of the time it's hanging out by the non-metal, right? So non-metal has higher electron affinity and things like that, but because the probability theory in nature, at times there are chances that it could actually be between the two ions, meaning being shared. This is actually emphasized more on a graph on the next page. Are there any questions before I click? I saw some people still writing. So this is the graph in number 35 on the top page 268. I don't know why I always want to go there. We'll go this one for a while. We can see before we even look at the questions asked of us, we have electronegativity difference for the x-axis. We have percent ionic character for the y-axis. So if you want to think about covalent character, it's the opposite. If we have 0 ionic, that means we'd have 100% covalent. If we had 100% ionic, that would mean 0% covalent. When we look at what the author decided to put on this table, if we have a large electronegativity difference, we tend to have a higher percent ionic character, and those are things that we typically think of as ionic. If we have a lower electronegativity difference, we have a low percent ionic character, but not 0, for most of them. And those are things that you would typically think of as covalent, although I know 3 of them, if you put them in water, you're thinking those are strong acids. That's a totally different idea, okay? And then, of course, we have our diatomic chlorine, or any of our diatomic elements would hit 0 difference in electronegativity and 0% ionic character because it is a nonpolar covalent bond. So how good is this approximation using difference in electronegativity as a measure of percent ionic character using the figure? We see ionic compounds with a high percent ionic character and also have a high difference in electronegativity. So yeah, it makes sense. If we have a low difference in electronegativity, we have a lower percent ionic character. Those are things that you think of as covalent. Is there a compound which has a 100% ionic bond? No. Some students in the past have tried to argue, well, the author cropped it, and he's hiding stuff from us. If you look at the slope of that red line, it's going to 0, to a peak. You know, so it's not heading up and he cropped the image. The peak is, we're getting up to that peak well before 100%. And again, that's because of the probability nature of our theory. There just could be times when that electron we're assuming is being transferred for ionic is actually being shared a little bit. Is there a molecule which has a 100% covalent bond, meaning 0% ionic? Yes. We have the diatomic chlorine noted here. I said any of our diatomic elements would be at 0, 0. Any questions? Number 36, I put in the electronegativity list. We're actually going to help you hopefully see how electronegativity relates to oxidation numbers. Something I don't have a slide for, I'm just going to leave that there. Something you really didn't like as far as, it's a traditional thing. Most 1 or 2 students don't like oxidation numbers. We're also going to extend that to a molecule where we couldn't have used our rules before. So instead of using the Lewis structure for NO2, I wanted to do a little bit of review of our rules. So I forgot the minus, NO2 minus, our nitrite. Per our rules, remember oxygen is usually -2 unless it doesn't work, right? So if I put a -2 there, we have 2 of them, which means overall we have -4. Therefore, what does the nitrogen have to be? What was that? +3? Because we have this negative here, we have to preserve, right? So -4, we keep that negative, we have -3. Therefore, that's +3. Let's see if we can actually see this +3 and -2 in a Lewis structure. And I actually have to draw 2 of them to be accurate with this, although I know the author only put 1 structure. This is the place where the theory doesn't always work perfectly. Some things we have to actually draw more than one Lewis structure, then almost imagine a blending of the two. Those are residence structures. We'll talk more about them after the break, but there are two different ways that we can draw the Lewis structure, and actually nitrite itself doesn't look like this, it doesn't look like this. It looks like a blending of the two. Meaning if I had transparency film and I had one of them printed on one page, the other one printed on the other page, and I overlaid them, that's kind of what it would look like. Needed to help you see the -2 on each oxygen and the +3. So let's say label that one oxygen 1, which means down here, that's also oxygen 1. The only thing that's moving are the electrons. They are labeled as oxygen 2. If we just look at the top structure and think about electronegativity, which element is more electronegative, nitrogen or oxygen? Oxygen, right? Whatever's closest to fluorine. Fluorine's the highest and oxygen's right next door, meaning the electrons in these bonds are going to get pulled towards that oxygen. Meaning it will be a little bit more negative, times 2, -2. You can also see that down here in oxygen 1 in the other structure. 2 arrows getting pulled towards that oxygen. The oxygen is a little bit more negative, times 2. I know it's a little messy when I put my arrows in. So our oxygen is -2. You can't see it with the single bond so much because you're thinking, okay, oxygen is more electronegative than nitrogen. I'm pulling down, but I only have 1 arrow. But when we think about the fact that the actual structures are blending of these two, we can see the -2 in the, I want to keep saying oxygen 1, in the left-hand structure, and we can see the -2 in the right-hand oxygen. As far as the nitrogen, we have to include the oxygen. We know that we'll have a pull towards that oxygen away from the nitrogen here, and we already have 2 other arrows. We're removing electron density times 3. Meaning it's going to become a little more positive 3 times. Meaning oxidation has to do with electronegativity, we just couldn't say that before. So let's apply this to a structure that we could not have used our rules for. The structure they have is at the bottom of page 268. I was stalling a bit because I had to change my page, and I saw people still writing. And I hate to flip the page when people are writing. Remember, I always have this up here. I'll take pictures if needed. So I'm going to redraw this, and they do have the carbons labeled. One is an A, the other one has a B. Oxygen, hydrogen. Another oxygen up here, and we have some more hydrogens. And I'm going to write out the formula. So we have CH3COOH. Using our rules, we can get some of it done. We can remember hydrogen. Hydrogen is +1 unless it's with a metal, right? Well, the carbons and the oxygens are all nonmetals, meaning all the hydrogens are +1. We could say oxygen -2. That's what she says always is, except unless it doesn't work. Since it's a neutral molecule, the numbers on the carbons would have to be equal but opposite, right? So that everything added up to 0. We right now have -4, and we have +4. Remember, we have 3 hydrogens where that one +1 is. Meaning, one of the carbons has to be plus something, the other carbon has to be minus something, then we don't have a way with the rules to figure that out. So let's use our Lewis structure. I know they have a little table for you, hydrogen, oxygen, carbon A, and carbon B. So let's just deal with carbon A right now. We know that the hydrogens are going to be +1, unless it doesn't work, unless it's with a metal. Well, and that's because the carbon is more electronegative than the hydrogen, and we'll have the pulling of the bonding electrons away from each hydrogen. We will also see that with this other guy over here. Oxygen is more electronegative than hydrogen, so we're going to have the bonding electrons pulled towards the oxygen. Every one of those hydrogens is +1. We can also see the -2 in the oxygens. This oxygen up here, double bond to the carbon. Well, it's more electronegative than carbon, meaning we will have a pull away from the carbon of those bonding electrons twice. And there's more negative charge, electrons getting pulled that way. Here we already have one arrow in place. If we put the other arrow in place, we have two sets of bonding electrons getting pulled towards the oxygen. Each oxygen is -2. Now that we have all of our arrows in place, noting the bond between the two carbons is nonpolar, we have 3 arrows on carbon A getting pulled towards it. Well, that means towards more electrons 3 times. -3. For carbon B, we have 3 arrows getting pulled away from the carbon, meaning the electrons are going away from it, making it more positive. 3 times. But there's no way you could have gotten that +3 to -3 out of using the rules. And I had to think about the Lewis structure, which is why I had to wait till now. Are there any questions? Yes.
So plus and minus for CA and CD table comes from which was more electronegative?
Where it comes from
CA is
what?
more electronegative, thus it has minus, and CD is.
Well, they're both carbon atoms. They have the same electronegativity. We have 3 sets of electrons getting pulled towards carbon A. It's more electrons negative, 3 times. We have 3 sets of electrons getting pulled away from carbon B. Less electronegative, not that. Less negative charge 3 times, therefore +3. Okay? Anybody else? The slide I have up goes with page 269. Hopefully writing Lewis structures has been something you've done in the past. There is a method on page 269, because it's been a long time. There's also a slightly different method in the textbook, page 299. Of course, you can use whatever method you were already taught. We're presenting the possibilities of these 2 methods for those that have spent a long time and you don't remember what you were taught. But we do assume it is review. Which means page 270, number 39, skip 40, and 41 to 44, I put in electroactivity pages. The reason why I skipped is there's a little typo in the actual writing of that chapter, summary chapter 9, that actually has you do a problem that hasn't been covered yet. So until that actually gets fixed, we're doing revisions right now, I have students skip that. So just 39, 41 through 44. Meaning, we're going to review a couple of things that you have to think about when you're writing a Lewis structure, just kind of making sure you're doing it right. And then a new way to evaluate if the Lewis structure is actually being done right, and if you can have more than one structure, which one's better. First off, when you're writing a Lewis structure, you need to make sure to use all of our valence electrons. We can't use too many or too few. We also have to make sure that the octet rule is being followed unless it can be broken. We know hydrogen never wants 8. Well, there's other things that don't want 8, or they might want more than 8. Nitrogen is not one of those things that breaks that octet rule. We'll be talking about that after the break. So, we need to think correct valence and octet rule for now unless we're told otherwise, except for hydrogen, which is a duet. So, for the, I'll just label them left versus right. What's wrong with the structure on the left? It is not correct for N2H4. N2O4 written down on the left. What's wrong? How many valence electrons do we need?
Nitrogen has 2 valence.
What's that?
Nitrogen has 2 valence.
Okay, nitrogen is in group 5, so it has 5 valence. And hydrogen is in group 1, each has 1 valence, so 5 times 2 would give us 10, plus 4 for each hydrogen, right? So for N2H5, we need to have 14 valence electrons shown. Remember, each line is 2. We have 1, 2, 3, 4, 5, 6 lines, meaning on the left-hand structure, we're only using 12 valence electrons. We have to use the total amount. So it's incorrect because it's incorrect number of valence. I don't know, I wrote that right there. I guess I'll put 9. I'll put right here. structure. Are we using the regular valence?
Yeah.
Got 7 lines. 7 times 2 is 14. We're good there.
Breaking the octet rule.
We're breaking the octet rule for the nitrogen. I said we can't do that with nitrogen. Each line representing 2 electrons, meaning if you count the lines going around each nitrogen, we have 5 lines, or 10 electrons. So the right one is we're breaking the octet rule. What about the correct Lewis structure? Lay out your central atoms symmetrically, and then we surround with what we call our terminal atoms. The hydrogen is never going to be in the middle, because they can only have 1 line. So we are going to just symmetrically put our hydrogens around our nitrogens. We're going to attach them so they don't fly away. I always say you need to bond at least 1 bond, make sure things aren't going to fly away. Count your bonds, 1, 2, 3, 4, 5. That's only 10 electrons, I need to use 14. What you do is you go from the outside in, distributing your extra valence electrons. Well, the hydrogens already are isoelectronic with helium. They have their duet, they have 2, so we can't put any extra electrons on the hydrogens. Meaning I'm going to put some there and some there. I now have my 5 lines, my 4 dots, I have 14 valence, and I have the octet on each nitrogen satisfied with 3 lines and a lone pair. They have 8 valence electrons around each. That's the correct structure, and yes, there's different ways you can draw it. As long as you have a lone pair on each nitrogen and 2 hydrogens on each nitrogen, with the nitrogens bound to each other, there are, yes, different ways you could draw that. We're going to introduce one other way we can evaluate a Lewis structure. It comes in very handy when you have more than one, and we'll be doing that when we come back to Thanksgiving break, but I thought, you know what, we can at least get to number 2, this definition, so that you kind of know what we're going into after the break. Bless you. Formal charge is defined as the, there we go, electrical charge difference between the valence electrons in an isolated atom and the number of electrons assigned to that atom in the Lewis structure. Meaning how much did we change the number of valence electrons? The way the formula is written, or equation, is C sub F, formal charge, equals number of valence electrons for that atom minus number of non-bonding electrons when you're in the Lewis structure. To this, we're adding 1/2 of the bonding electrons. Meaning, if we want to think about this nitrogen here, it's got 5 valence group 5, but to this we have 1, 2, 3, 4, 5, 6 bonding electrons and 2 non-bonding electrons. So to demonstrate this, it would be 5 minus 2 plus 1, 2, 3, 4, 6 divided by 2. 6 divided by 2 is 3, plus 2 is 5. So 5 minus 5 would give us 0 for that nitrogen or the other one. Doesn't matter which one it is. Meaning we really didn't change how many valence electrons we were actually assigning to that atom in the Lewis structure versus when it's by itself. Yes?
I missed the CS.
Formal charge. There's an easier way to think about this because this formula is usually not given.